In the 12th century, Belur served as the thriving heart of the Hoysala Empire. It is here that the builders constructed the Chenikeshava temple. Most visitors who walk through these doors see a masterpiece of religious devotion and artistic beauty. But look closely at the structural components, and the site reveals itself as a mechanical anomaly. Inside the main hall stand over 100 perfectly circular columns. Each features razor-sharp geometric profiles and a mirror-like polish that reflects the dim interior light. You cannot organically produce this level of flawless, continuous radial symmetry using only human muscle and a hand chisel. Consider the Narasimha Pillar. It weighs several tons and is almost entirely concealed by hundreds of complex miniature relief carvings. Yet structural evidence and historical records indicate that this massive, heavy stone column originally rotated smoothly on its central axis. Outside in the courtyard stands the gravity pillar. It rises 42 feet into the air, yet there is a visible gap beneath one of its corners, proving it rests freely on the surface without any mortar or a deep foundation. The existence of these artifacts points to specific problems the Hoysalas had already solved. To create them, they had to overcome extreme friction and manage multi-ton rotational weights, technical hurdles that would later take centuries to rediscover. The explanation for this level of precision begins with a specific geological quirk found in the local soil. The temples are constructed from a specific band of chloritic schist, commonly known as soapstone. When freshly quarried from the earth, this material is hyper-malleable, holding a consistency much like hard wax or dense clay. This yielding texture allowed artisans to bypass the limitations of brittle rock. They could carve jewelry, fingernails, and floral motifs with the precision normally reserved for ivory or wood. But the stone possesses a strange physical property. Upon prolonged exposure to the atmosphere, it oxidizes. The material slowly hardens until it reaches the strength of steel. This created a strict engineering deadline. The Hoysalas had to rapidly machine and shape the blocks while the stone was fresh, before the air locked their exact cuts into an indestructible fossilized state. If the material allowed for smooth shaping, there is still the problem of motion. Achieving perfectly concentric, polished stone columns requires high-speed rotational machining without the use of electricity. This diagram illustrates how the Hoysala engineers solved this with a heavy-duty, scaled-up lathe. They mounted raw, multi-ton rectangular blocks of stone horizontally on a central wooden axis, wrapping the mechanism in a thick rope pulley system. For a kinetic power source, they substituted an electrical motor with megaphona. Like tethering the ropes to walking elephants, they harnessed immense continuous torque to spin the heavy stone rapidly. As the blocks spun, artisans braced iron chisels against the surface. The rapid rotation sheared off the uneven edges, cleanly cutting perfectly concentric rings and bell-shaped profiles into the rock. We rely on motorized industrial machinery to shape raw materials today. The Hoysala builders reached the same level of mechanical precision by networking simple tools with animal labor. That explains how the pillars were shaped, but not how they moved after installation. A multi-ton flat stone cylinder cannot rotate smoothly against a flat stone base. The friction would simply lock it in place or shatter the joint. This cross-section shows the hidden mechanical solution utilized by the architects to make the Narasimha Pillar spin, an ancient ball-bearing mechanism. By placing perfectly spherical stone nodes within a carved track between the pillar and the floor, they displaced the immense vertical weight. This drastically reduced friction, allowing a single person to push and rotate the multi-ton column. This exactness in managing weight distribution also explains the 42-foot gravity pillar. Erecting towering monoliths without deep anchors requires flawless structural balance. The engineers utilized a principle known as the Meru Prasada model. Instead of fighting gravity with sheer mass, the structure tapers, incrementally transferring the vertical load outward and downward. To support this, they placed the temples on wide, star-shaped platforms called stellate bases. This geometry significantly lowered the entire structure's center of gravity and provided natural damping against seismic tremors. The survival of these structures relies on absolute mastery over geometric physics and weight distribution, rather than brute force or deep anchoring. The Hoysala Empire's golden age of engineering met an abrupt end amid the violent invasions of the Deccan Plateau in the 13th and 14th centuries. During this tumultuous period, the highly specialized knowledge required to build megafauna lathes, frictionless bearings, and interlocking stone joints vanished entirely from the historical record. The techniques were so thoroughly lost that later powerful empires like Vijayanagara could not replicate them. Instead, they scavenged the surviving columns from abandoned sites, treating them merely as valuable collector's items. We often view history as a straight line, assuming that human technology progresses slowly and steadily from primitive tools to modern industry. The Chenikeshava Temple stands as the primary record of this engineering era. It remains a testament to a period when builders solved complex mechanical problems through geometry and animal power, leaving behind a level of precision that their successors could no longer achieve.